In this lesson, we'll look at how to evaluate limits analytically or algebraically, not having to use a graph or a table. And we saw this in the previous lesson, and we evaluated the limit at 2 numerically. We also saw that if we substituted 2 into the function, I guess I better write the function. If we put 2 here, we get 0. 2 here, we get 0. So when we get 0 over 0, that's what it looks like on the graph. It's just an open circle. It's not an asymptote. To get an asymptote, here at -2, if we put a -2 in the numerator, we don't get 0. We get -4. But -2 in the denominator is 0. So when you have a non-zero number over 0, that will be a vertical asymptote. But when it's 0 over 0, there's just a missing point. And this is called an indeterminate form of a limit. It doesn't give us a value. It doesn't tell us if there's an asymptote, or it doesn't tell us the limit. So what we can do is, when this happens, we will be able to cancel something. So if we factored the denominator is x plus 2, x minus 2, and the numerator is x minus 2. And so we can cancel x minus 2, leaving 1 over x plus 2. And sometimes there are questions like, find a function that agrees with f at all points except for 1 point. And that's just a way of saying cancel and rewrite it. When we graph this function, there is a vertical asymptote, but we never get 0 over 0, so there's no missing point. And today we're just going to focus on this. So when we get an indeterminate form, we'll just cancel in some way, either by factoring or rationalizing, and then we can evaluate with substitution. And also remember that before we do anything to evaluate a limit, we just substitute. So here we won't have any division by 0. We can just substitute, and we know the limit. The limit is just the value of the function. We also have questions like this. So we're given the value of 2 limits, and then we're supposed to evaluate combinations and compositions of functions. I guess we could see if we can fit D in there, and that is the quotient. And so we just want to make sure we can use this concept. The limit can just be moved to any part of this. So I could write it as 4 times, then put the limit on the f. Limit as x goes to c of f. And then we just find, we can substitute, because we know the limit of f is 3/2. And that gives us 6. So here we can, that should be like that. limit of f and then limit of g. So the limit of f is 3/2 and the limit of g is 1/2, 4/2. So here we have limit of f times limit of g. So for part C, we do limit of f is 3/2. Limit of g is 1/2. So we get 3/4. And here we have limit of f, 3/2, limit of g, 1/2, and we get 3. All right, so we always substitute first. Two minus 2 over 2 squared minus 4, and we get 0/0. That's indeterminate, so we have to try to cancel. This is like the one we saw in the beginning. We just have to remember that we can change the order of subtraction if we factor out a negative. So if we left it as 2 minus x, it wouldn't cancel with x minus 2. Here we can now cancel. So we'll have limit as x goes to 2, -1/x plus 2, and we get -1/4. All right, pause the video and try that one. If we substitute, we'll get 0/0, indeterminate form, or an indeterminate form. So then we factor. And we have to multiply to get +4 and add to get -5. Here we'll have -4, +2, multiply to get -8, add to get -2, and common factor. Then we can substitute 4 minus 1 and 4 plus 2. Okay, so now if you have radicals, we still want to substitute to see if it is indeterminate. If we substitute a 0, we have radical 2 minus radical 2 is 0, and we have 0. Because it's indeterminate, we have to try to cancel. And here's our strategy for dealing with radicals. We are rationalizing the numerator, and we're going to multiply by the conjugate of the numerator. Wherever the radical is, if the radical is in the numerator, then we would do the conjugate of that. We could also have a radical in the denominator. Usually we wouldn't, though. All right, we don't change the sign of, we don't change the operation of the radicand. That's the inside of the radical. We have to change what's between the two terms. So when we do that and we multiply the two radicals, we have 2 plus x so radical times radical, the radicals cancel, and then we're going to have radical times radical, and that's a negative, and then we have a positive, so that's going to be 0, and then radical times radical, they cancel, we get a 2, and it'll be negative. Let's not distribute in the denominator, and we'll leave it like that, because what's happening is now we have 2 minus 2 is 0, and x is left in the numerator. So the x's cancel, and we have 1 over, substituting 0, we have 2 radical 2. And we can rewrite that as radical 2 over 4, because we would rationalize the denominator. So this is a 2 times 2 is 4, and then we're done. If you're wondering where this came from, you could write it like this. And we're multiplying all of this times all of that. So this would be 2 plus x minus radical 2, 2 plus x plus radical 2. Multiplying these, we get that. Over here we'll have negative radical 2, and then radical 2 plus x. Here's positive radical 2 times radical 2 plus x. And then these multiply to get negative 2. Here we have the positive of this and the negative of that. So they add to get 0, and that's where that 0 came from. Okay, pause the video and try this one. So we substitute first. 3 plus 1 is 4. Radical 4 is 2. 2 minus 2 is 0. We would have 0. Put a 3 in the denominator and we have 0. So we know we have to rationalize. We don't change this operation, we change this operation, change that, and that's what creates the cancellation in the numerator. So we have radical times radical, we have a negative 2 radical, a positive 2 radical, that's 0, and then minus 4. So in the numerator we have x minus 3. So x minus 3 cancels with x minus 3. And then we can substitute. There's a 1 left in the numerator. And that'll be 4. Radical 4 is 2. 2 plus 2 is 4. Okay, let's just do some work with some trig functions. We have two theorems, and we saw this in the previous lesson. We looked at it numerically, and we saw that the limit is 1. There's also a theorem for cosine. And then we'll just manipulate functions to make them look like this so that we can evaluate the limit. Well, this doesn't look like that, but if we can make it look like that, then we can evaluate it. So, if that were a 5, and I said 5x and 5x, well then now it's the same thing, and that's what we have here, x and x. As long as this is the same as this, then we can evaluate. So we want there to be a 5 down here, and then these will be the same. So let's just multiply by 5 over 5, and that will create a 5x in the denominator. So this 5 I just wrote in the front, and this is changing the denominator. Now we have the same factor, the same amount, quantity, numerator and denominator. So now we can use the formula. The limit, or the theorem, the limit can be applied just to this, and then the 5 is on the outside. So it's 5, and the limit of this is 1. So the answer is 5. Okay, pause the video and try that one. We need these to be the same, so this has to be a 3x, or this has to be an x. Well, it's going to be easier to make this x rather than make that a 3x. So let's just put that 1/3 out in front. And the limit of sine x over x is 1. So we have 1/3 times 1. And the limit is 1/3. All right, now we're still going to use the same theorem. So pause the video and try that one. If we do direct substitution, we have a 0 here, tangent of 0 is 0, and cosine of 0 is 1. So we'll still have 0 over 0. We can't evaluate with substitution, so let's try to rewrite. Our goal is to get sine x over x, or sine theta over theta somewhere. We have the theta in the denominator. Can we make the numerator look like this? Well, let's rewrite that. And now we see that, and we have sine theta over theta, and that's 1. Okay, if we substitute a 0 here, we have 1. 1 minus 1 is 0 over 0. That's indeterminate. So we see that cosine. We're looking for this function. We need to make this look like that. Well, that's pretty close. What if we try 1 minus cosine over h? That's what we want to have. And then just break up this square. So we have, instead of writing it as a square, we write 2 factors. Oops, that's supposed to be 1 minus cosine. Alright, this we know is 0, and this is 0. And it's okay to have 0 times 0. So using the limit, we know that this goes to 0 by the theorem. This is, the limit of this is 0, and putting a 0 here, we get 1 minus 1. 0 times 0 is not indeterminate, so we know the limit is 0. Alright, pause the video, try that one. We know we want to have this. Looks like we can get that, and we know that goes to 0. If we substitute a 0, here will be 1, and 1 minus 1 is 0. We get indeterminate form. So let's work on rewriting the function, and that's factorable. 1 plus cosine, 1 minus cosine. And let's start to group it like this so that we can see 1 minus cosine x over x. We know that equals 0, and this equals 2. 2 times 0. Substituting a 0 here, we get 1 plus 1 is 2. Substituting a 0 here, by the theorem, this equals 0. So the limit is 0. Okay, and we're going to stop there.